Hello, am I audible to all? Hello, 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 hello. एक second please. Hello, 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 hello. अरे इसमें कोई टेक्निकल प्रॉब्लम है, मैं माइक म्यूट कर रहा हूँ तब भी देखो आवाज ले रहा है, पता नहीं कैसे। हाँ माइक म्यूट है मेरा। हेलो हेलो, आप ठीक है? हाँ। चलिए, कोई बात नहीं, छोटा सा ग्लिच था, ठीक करा लिया। गुड इवनिंग एवरीबॉडी। सो दिस इज माय लेक्चर नंबर 6 और आज हम बात करेंगे ग्रेन साइज डिस्ट्रीब्यूशन के ऊपर। लेट अस स्टार्ट। बहुत इंटरेस्टिंग सा टॉपिक लेके आया हूँ आज आपके लिए, दैट इज द ग्रेन साइज डिस्ट्रीब्यूशन। ठीक है, काफी बार इसमें भी क्वेश्चंस आए हैं और इंटरेस्टिंग टॉपिक भी है। ये एक्सपेरिमेंट आपने जो है देखा भी होगा और अपने जियोटेक के लैब में किया भी होगा। उसी इंडेक्स प्रॉपर्टीज, ये एक टाइप की इंडेक्स प्रॉपर्टीज है, दैट इज वी विल डिटरमाइन हियर। So this is my grain size distribution. Okay. Let us start then. Grain size distribution. Today's topic would be grain size distribution. Okay. Today's topic is grain size distribution. So grain size distribution, what we do in this grain size distribution, we will separate out the soil into various size fraction and we will try to determine percentage of each size in my given soil sample, and the whole data will then be plotted on a grain size distribution curve. So let's see how we will separate out the soil into various size fraction and how we will plot this grain size distribution curve. So in this analysis, we separate out the soil into different size fraction based on particle size and find out the proportion of each size of particle in given mass of dry soil, and the result is then plotted on a grain size distribution curve. Now this grain size distribution is important for coarse grained soil. So the grain size distribution is more applicable or will alter the engineering behavior of a coarse grained soil. Fine grained soil properties is also affected, but to a very less extent. Fine grained soil properties, we have seen that it more depends upon the water content, like clays. Clays are fine grained soil. If you add excess amount of water, the clay will become change into liquid state or very soft. And as you dry the clay will become stiff. So the engineering property of my fine grained soil depends more on water content. Whereas the coarse grained soil property will depend upon the grain size distribution. How the engineering property depends upon the grain size distribution? Let us see this. Then I will show you how to determine the grain size distribution curve for a given soil. See, you have various kinds of grain size distribution. Either the soil can be well graded. Well graded means almost all sizes are present. Or we can have poorly graded soil or uniformly graded, when majority of the particles are of same size. You can see majority of particles are of same size. Then it is known as uniformly graded or poorly graded. And if almost all sizes are present, then it is known as well graded or non-uniformly graded. Non-uniformly graded because sizes are non-uniform. Okay. Then we can have gap graded also. Means if some sizes are missing, either you have very large size or very small size. These middle sizes are missing. So that kind of soil is known as gap graded soil. See, now if a coarse grained soil is well graded, you can compact it to a very large extent. Hai na? A well graded soil will look like this, a well graded soil will look like this. The number of voids will be very less here. So you can compact it to a very large extent, the strength of the soil will be very high. In poorly graded soil, you will see large number of voids, and this is how gap graded soil will look like. Okay. So engineering behavior of a coarse grained soil will then depend upon gradation. If you have well graded soil, you can compact it to a larger density, thereby giving us good strength. Poorly graded soil will have large permeability through it, but it can't be compacted to a large extent. Same goes for the gap graded. Okay. So like this, engineering behavior depends upon the grain size distribution for a coarse grained soil. So fine grained soil properties are affected more by interparticle forces and presence of water content, like I said you. Fine grained soil properties depends more on the more by interparticle forces, presence of water, etc. GSD helps in identifying gradation and uniformity of soil, the knowledge of which is used in embankment construction, filter design, etc. So our GSD will help in identifying gradation as well as uniformity of soil, whether the soil is uniformly graded, well graded or poorly graded, and the knowledge of which will be used in embankment construction. Like for embankment construction, you are making an earthen embankment with the help of soil. So there you have to densify the soil to a very large extent. So there we will go for a well graded soil. Got my point? Or we can have it for filter design. We are talking about sand filter. In the sand filters, we have to design the voids in such a way such that water passes through the filter, but impurities does not pass. Means the void sizes should not be very large and it should not be very small as well. So it should neither be very large nor be very small. The size of voids we can control with the help of this grain size distribution only. Got my point? Very simple till here. Any doubts till here? I am proceeding now. Now, the various type of gradation I have already shown you. These are the various type of gradation that we have to find here. Now, according to the size, how the soil is classified, first see. So, to classify the soil, we categorize it according to the size. How? Let's see this as well. Please focus here now. According to the size, how we have classified the soil. Let's see this as well. How we have classified the soil as well. So, here we have size. If size is greater than 300 mm, the soil is known as boulders. These are known as what? Boulders. If size is between 80 mm to 300 mm, then the soil is known as cobbles. If size is between 4.75 mm to 80 mm, then it is known as gravel. So these boulders and cobbles are not soil, they are just large stones. Now soil will start. So if size is between 4.75 mm to 80 mm, then it is gravels. Okay. If size is between 75 microns to 4.75 mm, then it is known as sand. If size is between 2 microns to 75 microns, 1 micron is 10 to the power minus 6 meters, okay, then it is silt. And lastly, if size is less than 2 microns, then it is known as clay. So, gravels and sand are coarse grained soil, particles that can be seen with the naked eye. And silt and clays, fine grained soil. These particles are not visible to naked eye. So, coarse grained particles are particles that can be seen with the naked eye. See, a normal human eye can only see particles which are having size greater than 75 microns. So, coarse grained soil particles have size greater than 75 microns. So, these particles can be seen with the help of the naked eye. So, here we can see the particles, but in the case of fine grained soil, you won't be able to see the individual particles. Got my point? Now, how this GSD curve is determined? GSD is determined using two methods. One is the now how this GSD is determined? GSD is determined either using the sieve analysis or by using the sedimentation analysis. So today I would be covering only the sieve analysis in detail. Sedimentation analysis is not that important. So for the coarse grained soil, the GSD determined using the sieve analysis. So let us see the sieve analysis in detail today. Any doubts still here? Please ask me. You can take a note. If you have any doubts still here, please ask me. Okay. Now we will see the sieve analysis in detail. Please tell me. Now let's see the sieve analysis. So what do you understand by a sieve? You have seen in your home also, this is a sieve. These have very small square openings like this through which the particles can pass. So this is my sieve and the size of the sieve is this. So here if I zoom this square, so this is my sieve size. This is known as sieve size. Now first what you will do, you will arrange this sieve in a decreasing order. Means the largest sieve will be on the top and the smallest sieve will be on the bottom. So let me say 80 mm is the sieve of the largest size and 75 micron is the smallest sieve. You will arrange this sieve in the decreasing order here. Okay, you will arrange this sieve in a decreasing order on this vibrator. And then you have a pan also which will collect the particles that are finer than 75 microns, as simple as that. Then you will on this shaker after pouring a dry soil. So you will take a dry soil sample, say 1 kg dry soil sample, you have taken dry soil sample. You will pour it on the top sieve and then you will on this shaker, it will start vibrating. The moment you put on this shaker, it will start vibrating and the particles will start sieving. So this will collect particles greater than 80 mm, then so on, and the particles will start sieving here. So after all the particles have sieved, you will dismantle all the trays and you will find out the weight retained on each sieve. And using that data, we will be plotting the grain size distribution curve. How? It I will show through a numerical example. See here, you have coarse sieves as well as fine sieves. Coarse sieves have size greater than 4.75 mm. Fine sieves have size between 75 micron and greater than, and less than 4.75 mm. See, these coarse sieves will collect gravels. These both will collect coarse grained soil only. For fine grained soil, sieve analysis will not work. For coarse sieves, collect gravel particles, which have size 4.75 mm to 8 mm. Whereas these fine sieve trays will collect what? This will be 2 mm and 1 mm, not 200 micron. Misprint is there. These fine sieves will collect sand particles. These fine sieves will collect sand particles and this coarse sieves will collect gravel particles. Okay. Got it? Okay. Now let's see, let's arrange the data here. Let's arrange the data here. Weight of dry soil is 1000 grams. Sieve size, let's take a weight of 1000 gram of soil and I will give you a data. Using that data, we will do all the calculation and then we will plot the grain size distribution. So let's start, my dear friends. So sieve size data for 80 mm. See, we had many. See, you don't have to remember the size of the sieves. Nobody will ask you. Just I have given these size. These are Indian standard sieves. So that we can solve a question on the same. Thus, there can be sieves between these sizes also. There can be more number of sieves between these sizes also, but you don't have to remember the sizes. Nobody will ask you. Don't worry. So 80, 20, 10, 80, 20, 10 mm, 4.75 mm, 2 mm, 1 mm, 600 microns, 450 microns, 212 microns, 150 microns, and lastly 75 microns. Okay. Finer than 75 microns will be collected on the sieve tray itself. Okay. Got it? Very good. Now weight retained on each sieve. This data was given to me. 250, 150. This data I am giving you. 250, 150. Then we will start our calculation. 50, 100, 50, 75. 50. All is in grams. 100, 50, 75. Then 25, 50, 25. 25, 50, 25 and lastly 15. Just sum it up please. Tell me what is the summation you are getting. If you will sum it up, you will get 790 grams. But total weight was 1000 grams. So where the remaining 210 grams gone? It is on the tray. They are fine grained particles. If you want to do the GSD of these fine grained particles, we have to go for the sedimentation analysis. Okay, no problem. So first I will find out the cumulative weight retained. Cumulative weight retained will be how much, my dear friend? Tell me fast. Cumulative weight retained. This is 200, 250, 400 grams, 450, 550, 600, 675. Okay. Then 700, 750, 775 and lastly we have 790. This is, I don't have space here, but this will be 790. Okay, this is 790. 790. I am writing here. Okay, this data I have written here, not a problem. Then percentage cumulative weight retained will be how much? 200. This will show me how much particles have size greater than 80 mm. Divided by total weight, that is 1000, into 100. That will be 20%. This will be 25%, 40, 45, 55, 60, 67.5, 70, 75, 77.5 and 79%. Then percentage final will be 100 minus cumulative weight retained. 100 minus 20 is 80%. Then we have 75%, 60%, 55%, 45%, 40%, 32.5%, 30%, 25%, 22.5%, 21%. So these are the percentage passing or the percentage final. Now let's plot this percentage final with the size of the particle, and for here we will see what and here we will see that this whole data is plotted on a semi-log paper. What is this semi-log paper? I will show you in detail. Okay. So what is this semi-log paper? We will see in detail. So this whole data will then be plotted on a semi-log paper. X-axis will be in the log scale and y-axis will be a normal scale. And this percentage finals is representing what? Particles that are smaller than 80 mm. So obviously if 20% particles are larger than 80 mm, the remaining 80% will be smaller than 80 mm. So therefore 100 minus percentage cumulative weight. Got my point? Very simple. Now let's plot this data, and from here you will get the GSD curve. Now a graph is plotted between the percentage final and the sieve size on a semi-log paper. So let's plot the graph on a semi-log paper we will plot the graph. Okay. On a semi-log paper, let's plot the graph. Let's plot the graph on a semi-log paper. Here I will take percentage final or percentage passing. And here I will take sieve size. And we will plot all the percentage final as well as sieve size, and you will get a S type curve. Here you will get a, though I will plot the points first and then you will get this graph, but I am doing in a reverse manner now. But first you should plot the points. So all the points I will show you, like for 80% we have many points are there, so that I will show first. So using this data I will get this GSD curve. So when you will plot all the points, you will get the GSD curve. Like here I have many points. For 80 mm size, the percentage passing is 80%. So 80%, this is 80 mm size. Then for 20 mm we have 75%. Then for 60% you have 10 mm. Then I will take the data for 30%, that is 450 microns. Rest all the data are also will be there, don't worry. One more data you take for 21%, that is 75 microns. Not a problem. And you will join these all points and you will get the GSD curve. So this is my GSD curve. Few things you have to note here, my dear friend. What? This is what? This is my GSD curve. Now, few things you should note here. First, I will show you what is D60. D60 is the size of particles such that 60% particles are finer than that size. That is corresponding to 60% finer. What is the size? That is D60. That is 10 mm. Similarly, corresponding to D30, 30% we have 450 microns. See, this curve will always be increasing because we have done the experiment like that. This curve will always be an increasing curve as shown. This curve will always be an increasing curve. So, D60 will always be greater than D30. And D10 we can't calculate here because I don't have all the data, but D10 would be smaller than D30. This will always occur because the curve will always be an increasing curve. So, D60 is the size of particles such that 60% particles are finer than that side. D30 size of particles such that 30% particles are finer than that side. And lastly, D10. D10 is also known as effective size of the particles. Not a problem. So, this is how a semi-log paper will look like. This is how a semi-log paper will look like. See here, the range of size is very large. So, a normal graph sheet you can't use. See, I have to plot the clay particles. Clay particles is having size of 2 microns, and your gravels have a size of 80,000 microns. So, the range is very large, you can see. So, a normal graph sheet won't be able to accommodate this much range. So therefore, we have to go for a semi-log paper. Log is already calculated here. So here you can plot the clay size as well as the sand size. For example, clay is what? Less than 2 into 10 raised to power minus 3 mm, and here it is 80 mm. So here see, log is already calculated. This is 10 raised to power minus 4 mm minus 3 minus 2. See, log is, it will go on in power, 10 to the power 1, 10 to the power 0, sorry, 10 to the power 1, and lastly 10 to the power 2. So gravels will come here, then sand, then silt, then clay. Log is already calculated here. So you can easily plot all the sizes and corresponding percentage final and get the GSD curve. So why we have to use this special graph sheet? Because the range of size was very large. So this is the semi-log paper that I was talking about. This is how it looks like. You don't have to take down it in notes. Okay, just I have shown it what is a semi-log paper. So D60 is the size of particles such that 60% of soil particles are finer than that size. GSD curve can be used to identify the gradation of the coarse grained soil. The various type of curves that can be obtained are what? Now I will show you the various type of curves that can be obtained using the GSD curve, and seeing the shape of the curve we can say whether the soil is well graded, poorly graded or gap graded. Let's see. Please take it down till here. If any doubts you can ask me. Rest I will show you different types of GSD curve. So let's see what are the various types of GSD curve. Please take down till here. If you have any doubts, you can ask me. Okay. Please ask me if you have any doubts till here. गेट CSC के लिए I don't teach for CSC. These are classes are for civil engineering, my dear friends. My expertise is into civil engineering. So I would be covering your lectures for civil engineering only. Okay. So any doubts till here? Can I proceed further? Okay. Any doubts? So we have various kind of GSD curves that you can get here. Let me show you the various kinds of GSD curves. Let's see the various types of GSD curves that I can obtain. And you have to tell me which curve belongs to which category. See, when we have plotted we have various kinds of GSD curves here. What are the various types? Let's see. What are the various types of GSD curve here? Let's see. This is size versus percentage final. Okay. First curve that you are getting. This shows me a well graded soil, because almost all sizes are present. For every size you will get a percentage final. So this is a S type curve. It is a well graded soil. That means almost all sizes are present here. All sizes are present here. Then a poorly graded soil, primarily coarse grain. How would it look like? Let me show you. This is my 75 micron line. So if you get a vertical curve here like this, which shows me that majority of particles are of same size, then it is a gap graded soil. See a vertical curve, almost all sizes are uniform, very narrow range of sizes, and particle size is greater than 75 microns, so it is a coarse grade soil. Plus you can get this type of vertical curve on this side also. This is a primarily fine grained soil, again a poorly graded soil, but primarily fine grained. That is a C type, or it can be shown as uniformly graded as well. Then the last type of curve that we can have is a stepped curve like this. This tells me that the soil is gap graded. How? See, that I have to show you. The horizontal portion of this curve is actually the break of continuity. For the sake I am drawing the curve, but in this portion the curve is discontinuous. These sides are missing. How I am so confidently saying this? Let me show you. Say for example, for 40% passing, you have two sizes available, 1 mm as well as 2 mm. So for 1 mm as well as 2 mm sieve, your percentage passing is same. For this also 40% and for this also 40%. It can happen only when there is no retained on 1 mm sieve. It can happen when 0% retained here. Means we don't have any particle sizes that are we don't have any particle size between 1 mm to 2 mm. Here it is 0% retained. Got my point? So this you should understand here. So well graded soil, all sizes are present. Poorly graded soil or uniformly graded, majority portion of same size. And we have uniform poorly graded or uniformly graded or gap graded. Okay, and gap graded means some portions are missing. So the horizontal portion of the curve is what it is saying, that some sizes are missing. like I have shown in the example as well. Okay. Now, we are engineers, we see everything mathematically. So, mathematically, some shape parameters are defined. First shape parameter is known as coefficient of uniformity, and second one is known as coefficient of curvature. Seeing these values also, we can say whether the soil is well graded or poorly graded. How? The first shape parameters, so GSD curve is also used to find out certain shape parameters which are used in classification of soil. First one is coefficient of uniformity. Cu is what? Cu is D60 upon D10. Cu is what? D60 by D10, and Cu is always greater than or equal to 1 because D60 is always greater than D10. If Cu is equal to 1, the curve is purely vertical, and when D60 and D10 is same, D60 and D10 will be same only when the curve is purely vertical. See, for 60% also same size and for 10% also same size. That can happen only when the curve is vertical, that is all the particles are of same size. So, it is uniformly graded soil. As you increase the value of Cu, the range of size will increase, that is you will shift towards the S type curve. Then one more parameter is defined, that is coefficient of curvature, that is D30 square upon D60 into D10. This D30, D60, D10 we can obtain from the GSD curve only. And D10 is also known as the effective size of particle, that I have told you as well. This is also known as effective size of particle. Now, if Cu is greater than or equal to 4 and Cc is between 1 and 3, this limit you have to remember, then it is well graded gravel. Whereas, if Cu is greater than or equal to 6 and Cc is between 1 and 3, then it is known as well graded sand. This limit you have to remember, but I can tell you the logic why for gravel Cu is taken less and for sand Cu is taken as more. Why? See, in smaller sizes, the variety of sizes can be more, but for a large particles, the variety of sizes will be less. So, for gravels, generally Cu will come out lesser as compared to that in sand, because smaller the size, larger will be the variety of sizes. Larger is the variety of sizes, larger would be the value of Cu. So, larger the value of Cu, larger is the range of particles present. So, if any of this limit is not satisfied, then the soil is poorly graded. So, for well graded soil, Cc should be 1 and 3 and Cu should be greater than 4. Similarly, for well graded sand, Cu should be greater than or equal to 6 and Cc should be 1 and 3. Got it? Let us do a question on these concepts now. We have seen many things today. Let us do a question on this concept now. Let us see a concept here now. Very interesting concept I will show you. Now, let us see a question. A good question I will show you. Please note it down till here. If you have any doubts, you can ask me. Rest, you can start attempting this question. Please do this question. You have to find whether the soil is well graded sand or what it is. Okay. Poorly graded sand, you are getting what answer? Poorly graded sand? Let's see what was the correct answer. I had also solved it. Let me see the answer for you, my dear friends. Let's see the answer for you. Yeah. Yeah, it is poorly graded sand. Very good. This is poorly graded sand. B was the correct answer. Very good, Akash. Let's try to solve it. So, sieve analysis was conducted on a dry soil sample of mass 1000 grams. See, mass of the soil was how much? Total weight of the soil was 1000 grams. Okay. Now, it was said that D10 is 10% particles are finer than 0.15 mm. So, D10 was given to me as 0.15 mm. D30 is 0.3 mm. You can see that majority of particles are between 75 micron to 4.75 mm and 60% particles are finer than how much? D60 is 0.6 mm. This was given to me in the data. CuCC we have to find out. Classify the soil as well as per C. Majority of the particles have size between 75 micron to 4.7. Majority of the particles have this size only. This implies it is sand only, because I can say that majority, more than 50% of the particles have the size between 150 microns to 600 microns. Means it is between 75 micron to 4.75. That means it is sand. That is confirmed. Now for sand we have to see CuCC. Cu is how much? D60 by D10. How much Cu you have got, my dear friend? Tell me. 0.6 upon 0.15. That is 4. And Cc is D30 square. D10 into D60. 0.3 square upon 0.15 into 0.6. So Cc how much you are getting? Cc I got it as 1 only. So Cu is not greater than equal to 6 and Cc is between 1 and 3. So Cu is not greater than 6, that is it is less than 6. This implies what? Poorly graded sand represented by a symbol Sp. So like this you can do this question. So like this you can find out the gradation of the soil based on Cu as well as Cc. Okay, Mr. Akash, very good, my dear student. So B was the correct answer. So this was all about the sieve analysis. Tomorrow we will see the Atterberg limits in detail. So this is my Telegram channel. You can join me there if you have any query regarding your preparation. If you require any guidance or anything, you can always join with me on this Telegram channel. Rest these Telegram channels are also there for any notification regarding civil engineering. Okay, join the channels. All the very best, everybody. Bye bye.